All right, so in 5.2, we're going to look at an idea called Rolle's theorem and the mean value theorem. These are going to be things that kind of work like what we looked at last time, just using the derivative to find out other things. So what we looked at again way back at the beginning, first thing that the derivative let us do is find what kind of its purpose? Slope of the tangent line. So then what we looked at just a little bit ago is to find those critical values. Back in 5.1, we could find maxes and mins using the derivative. And this is going to give us some other places that we can use that. So first thing that's up here is Rolle's theorem and figure 5.8. The figure you do not need to write down because that's actually one that's in your book, so you can just look at that. But I do want you to write down Rolle's theorem. It says 3.3. I know in your book it says 5.3, just because this was pulled from the version of your book that does not have the pre-calculus stuff. Same deal. So Rolle's theorem states, let f be continuous on the closed interval, a to b, and differentiable on the open interval, a to b, if f of a is equal to f of b, then there is at least one number in that open interval, a to b, such that f prime of c is equal to 0. Now I'm going to go ahead and highlight a couple of things in here that are important. For us to be able to use this theorem, it's got to meet that hypothesis. There's two things that we have to check first. First thing, we've got to check, is it continuous on that closed interval? So continuity, visually we can check for that, no breaks, no gaps, that kind of stuff. And it needs to be differentiable on the open interval. So can you take the derivative wherever you want to? If both of those aren't true, then this theorem is not going to work. So if you look up there at the top one, that parabola there, from A to B, we've got a smooth, continuous curve. At every point, I would be able to take that derivative. So it's continuous and it's differential. However, on the second one, it is continuous because it goes from here to here. No holes or anything. But it's not differentiable because it's got that corner to it. So the theorem would apply to this one, would not apply to this one. So again, just kind of the big thing once you get so far is, to use this theorem, you got to be able to take the derivative everywhere, and that also does mean that it's continuous. It's got to be both of them. And that's just saying that somewhere in that interval, the derivative is going to be 0. So somewhere in that interval, there's a maximum in, as long as those 2 points are the same. The way I kind of like to think of it is if you've got two values that have the same output, you're going to have some symmetry. If you have symmetry somewhere between those 2 points, there's going to be a maximum or a minimum. And that's what this theorem is saying. If you've got 2 points that are symmetrical on some kind of interval, you're going to have some kind of a hill or some kind of a valley on the graph. So another one. Maybe pretty similar. All right, so in this case, I look at it, I can tell that's a polynomial. I don't have any division, I don't have any exponents, no radicals, nothing like that. So I know for sure that's continuous on the entire interval and differentiable on the entire interval, just by looking. And that's something you kind of get used to. If it's one like that, polynomial, you don't have to check. So the first thing we're going to do is differentiate. So we're going to take the derivative with respect to x. So f prime of x is going to be equal to, what rule am I using? Product and change, just like last time. So I'm going to have x minus 3 times, chain rule here. So I'm going to go ahead and move the 2 out in front just because that looks better. Times the x plus 1 times the derivative of the inside, which is just the 1, plus the other one. So it's going to be x plus 1 squared times the derivative of the other one, which is just 1. Now on the other one where I skip that work, I'm going to go ahead and walk through that. I'm going to expand this out. So actually FOIL here, FOIL there, combine like terms, and then refactor once it's all together. I'm going to get equals 2, FOIL, so x squared minus 3x plus x minus 3 plus, FOIL that one out as well, so x squared plus 2x plus 1. Either mentally kind of think about distributing the 2, which is what I'm going to do. So don't forget that we're doing that, but I'm not going to write it out. You got 2x squared plus another x squared, so that gives me 3x squared. I've got negative 6x plus 2x, so that gives me negative 4x, plus another 2x, so minus 2x. And then our constants, I've got negative 6 plus 1, so negative 5. So that is the simplified version of our derivative. Work with OK?
So you just started doing this and factoring in.
Mm-hmm. Now I'm going to set that derivative equal to 0. And that's why I'm going to want to factor. So we're thinking of factors that work for this. Anybody see them already? And I'm going to have to use a 3x here. And I'm going to use an x here.
Minus 5 plus 1.
Yep. One that we really didn't have any choice about at all. Worked out pretty nicely. The only factors are 3 or 3 and 1. Only factors are negative 5 or some combination of 5 and 1. So then solve each of those now. So our two solutions this way are going to be x equals negative 1 and x equals 5/3. Now again, we don't care about that negative 1 because it's part of the interval. So the answer that we're going to care about is C. Okay? And that's how those work. So again, first thing, verify that it's differentiable and continuous on the entire interval. Take the derivative, set the derivative equals 0, do whatever you need to do to solve. You know, in this case, we ended up factoring and then combining and refactoring, and then looking at which one is in between our two intervals. Now, some of them might be a little bit more work, like you could be a radical or some kind of rational, but just solve it however you normally do. You're still going to take the derivative. You're always going to set it equal to 0, and then just do whatever algebra you need to do to be able to solve. And that's how Rolle's theorem works. The next one is called the mean value theorem. And in mathematics, when we're talking about the mean, what's that another word for? The average. And that's exactly the same context that it's referring to here as well. If f of x is a differentiable function over the closed interval a to b, then at some point between a and b, f of b minus f of a over b minus a equals f prime of c. As we go through this, I'm going to give you some fairly concrete examples, even though I'm guessing at this point that looks like it doesn't make a whole lot of sense at all. It's actually a really straightforward concept. I think you'll latch onto it pretty easily. So a few things that we can say about this. First thing, just kind of a reminder, differentiable implies that the function is continuous. That's based off of our initial definition of derivative. To be able to have a derivative everywhere, it has to be continuous everywhere. The other way around is not necessarily true. But to be able to take the derivative, it had to be continuous. The mean value theorem only applies over a closed interval. So that's another big restriction for it. You do have to have set limitations. And those limitations have to include the endpoints. Then here's the big deal. This is the most important thing I'm going to tell you about this. The mean value theorem says that at some point in the closed interval, the actual slope equals the average slope. Again, at some point in the closed interval, the actual slope equals the average slope. So what we're going to do is look back up at that equation and just kind of write it out a little bit more. This part over here, that is the average slope. Because basically, what is that right there? I'm just on the left side. Back to algebra 1, something you learned there. Instead of f of b minus f of a, you probably saw y2 minus y1. And instead of b minus a, you probably saw x2 minus x1.
If the a, b, and c is the same thing, is that like in standard form?
This is just saying random point A, random point B. That happen to be the interval that we're looking at. Slope formula. Okay? So what I circled there, that's just the slope formula. And that's what you do when you're finding the slope between 2 points using that. You're finding the average rate of change. And it worked on a line all the time because the average rate of change was always the instantaneous. Like we looked on a curve, remember back to when we first looked at the tangent line problem, we kind of estimated by making secant lines over and over again, it got closer and closer to the tangent line. What this is saying, at some point, that average is going to be the actual, which is this side. Remember, our derivative gives us what the exact slope is. So the mean value theorem says at some point, the average and the actual have to be the same. That's what I'm kind of talking about. That kind of makes sense. And we'll look at some problems where it kind of has to work out like that. But if something is your average, at some point, even if it's only for an instant, the average and the actual are going to match up. And that's where this kind of comes in handy. The next thing that's going to pop up here is a graphic that's in your book. So again, you don't have to write it down. Just look. But it just kind of shows you on, we've got this curve here. The tangent line, again, remember the tangent goes through only at one point. Well, at some point on this interval, what do you notice about the tangent line and the secant line? Like how do they relate to each other? They're parallel. If they're parallel, they have the same slope. So it would meet the mean value.